All right, so for the second part of the problem, we are asked to obtain what is going to be the total charge within the sphere of a radius r equals to 3. So here we will use the Gauss law that states that flux equals to the closed surface integral of d times ds equals to 0. So we already know what are these elements. We know that the flux density d is going to be given as 0.3 radius square, AR direction, given in nanocoulombs per square meter. However, since we are working with nanocoulombs, it's going to be the same if we place it as times 10 at minus 9 radius square in the AR direction. We just erase this nano from here. This is going to be our flux density expression. Then, to fully complete this integral, we need to know what's the ds. And we know that ds for spherical coordinates is going to be r squared sine of theta d phi. This is going to be our differential surface element. We will use directly this part, this q. We use directly this part right here. So we got the closed surface integral, which is a double integral from 0 to pi for theta, from 0 to 2 pi for phi. We replace the values. We know our flux density is going to be 0.3 times 10 at minus 9 radius square AR dot product radius square sine of theta d phi. Now, this is also in the AR direction. How do we eliminate that? Well, we see there is a dot product in here. We can make the dot product between these two. And since they're going to the same direction, they're going to be equal to 1. Similar to what happens when we try to dot product I dot product I. It's going to be 1. J dot product J. It's going to be 1. So AR dot product AR, it's going to be 1. We just erase them from here. Rearrange, and we will make some considerations. Look, we got radius square times radius square. That means we can erase this and elevate this at radius 4. We're just simplifying the equation. Second, we're going to integrate only about the elements of the differential elements. That means all the thetas and all the phis. Since any of these expressions actually contain a theta or a phi, it can go outside of the total integration. So 0.3 times 10 at minus 9 radius 4 times the integral from 0 to pi, integral from 0 to 2 pi, sine of theta d phi. This is going to be the integral we need to actually solve. Let's reduce everything in here a little bit so we can make space to keep solving. Now, we will take this element right here and we're going to start integrating from the easiest. Which is going to be the easiest? Well, this one combined with this one. This integration of phi only contains d phi. That means the integration is going to be phi evaluated from 0 to 2 pi. So we can write the whole expression as 0.3 times 10 at minus 9 radius 4 integration 0 on pi times phi evaluated from 0 to pi times sine of theta d theta. Now, this one right here, when we evaluate a constant from 0 to any number, we just replace it by the number of it on the upper limit. That means this one right here becomes 2 pi. Since 2 pi is actually a constant, it can go outside too. So we will get 0.3 times 10 at minus 9 or at 4, 2 pi integration 0 to pi of sine of theta d theta. And the integration of sine of theta about d theta, it's going to be minus cosine of theta. So we can write it down as 0.3 times 10 at minus 9 radius 4 2 pi minus cosine of theta evaluated from 0 to pi. If that's the case, erase on this section right here and open some space to keep working. If we evaluate minus cosine of theta from 0 to pi, well, we remember that cosine of pi is actually minus 1 and cosine of 0 is actually 1. So the evaluation will end up being 0.3 times 10 at minus 9 radius 4 to pi times minus 1 minus 1, delivering 1 and 1 added, and this 1 and 1 added is going to be equal to 2. So we can just erase everything in here and place a plus 2 in here. In conclusion, we will have that the total amount of charge within the sphere of radio equals to 3. It's going to be 0.3 times 10 at minus 9 radius at 4 pi. The AR direction, coulombs by square meter. Now, if we want to know at a specific radius, we just replace it. So this charge will be 0.3 times 10 at minus 9 times 3 at 4 pi. And the result for that, it's going to be 305 nanocoulombs. This is going to be actually like this. Nanocoulombs. Now, this is the answer for the part B. However, we came out with an expression of Q that we can reuse for the next exercise. I'm just going to save it for later. So if we advance for the second problem, we have exactly the same flux density, but now we're asked for the flux limit sphere of radius 4. As we remember for the Gauss law and from Faraday experiments, flux equals charge, and we know charge is going to be equal to this. So we just take this expression and replace the values. You just make little adjustment. This 2 pi times 2, it's actually going to become 4 pi. And if we want to know the flux at radius equals 4, which is the one in here, we substitute 0.3 times 10 at minus 9, radius of 4 at 4 times 4 pi. We remember this is in the AR direction and it's going to be given in coulombs. Coulombs. The answer for this is going to be 965 coulombs, nanocoulombs. Where that nanocoulomb becomes of this. We get this answer.